Ruchika, who has a lot of expertise on phenomenological insights from data.
First, I would like to thank all the organizers for bringing all the community together, and we are having this nice discussion about cosmological tensions. And then I would like to thank Tanvi for introducing me. So usually I work in cosmological tensions, and I try to propose models which can alleviate tensions between high redshift observations and extremely low redshift observations, such as reanalyzing the standard distance ladder or inverse distance ladder by seeing what can new physics be there which can help to alleviate the tensions. But today I will be talking about a very interesting anomaly which is within BAO and which has not been talked into the community much. So I want to stress on this anomaly within BAO between 2D and 3D measurements. So this is basic outline of my talk. First, I start with Planck 2018 results, which utilize CMB, BAO, and supernova. And then I'll go ahead with talking about the tensions in lambda-CDM cosmology. And then I will talk about how important BAO is and how it suggests the need for introducing the early dark energy. Then I'll go ahead with talking about the anomaly between the BAO. What's important here is when we are talking about cosmological tensions, those tensions are measured when we are measuring those measurements at different redshift far away. But at BAO, we are measuring exactly at the same redshift in 2D and 3D BAO, around redshift of 0.51 to redshift 2, and still we are getting different results. So this should be stressed, so that's why I want to present this work today. And then I will also include the DESI BAO analysis, and then I'll just conclude my talk. So these are the results from Planck 2018. So they have taken the CPL parameterization, and this is W0WA contour. So you can see here when they are taking just Planck data, the contours are really big, but as soon as they include the weak lensing and redshift space distortion, the contour gets small. But when they include BAO and supernova, the contours get even smaller, and you can see still the W0WA, which is -1 and 0, is quite agreement with the lambda-CDM. So if all the cleaner probes, which is supernova, BAO, and CMB, shows that the lambda-CDM is valid, then why we need to go beyond lambda-CDM? So cosmological constant is consistent with CMB, BAO, and supernova, then why we need to go beyond lambda-CDM? So as I think all these tensions have been talked, people have given great talks yesterday and today about all these tensions in lambda-CDM relating to Hubble tension and the growth tension, cosmic dipole tension, and then CMB anomalies. And we can see all these anomalies, like in CMB anomalies, they are measuring at different multipoles. Hubble tension is also at redshift 1100 and redshift less than 0.15 for the growth tension. So all these are different, either multipoles or different redshifts. But in BAO, we are measuring exactly at the same redshift, and still we are getting different results. So the present situation is, if we say among all these tensions, the most known or more than 5 sigma tension is the Hubble tension. And so what is about Hubble tension? A brief introduction is like when we are measuring exactly using parallax or supernova, using Cepheids and supernova, we are getting the value of H0 around 73 plus minus 1.04. So we don't assume any cosmological model here, we just assume the cosmographic series, which is just something like Taylor expansion, so there is no cosmological model involved. But when we are measuring the same Hubble expansion constant, Hubble parameter at present around the redshift of 1100 from CMB, we need to assume a model, cosmological model, and Planck assumes lambda-CDM. They are getting this value of H0 more than 5 sigma away. And this is Hubble tension. So the main point is no matter where we are measuring the expansion rate of universe, like Hubble constant, all the probes should give the same value. But these are in very disagreement with each other, another clean probe at present is baryon acoustic oscillation. So what does baryon acoustic oscillation say about this picture? What and how BAO adds to the present situation? So before talking about the BAO anomalies, I would like to take you like 5 years ago when BAO was considered like BAO was a probe which actually suggests us to look for the early universe solutions or early dark energy solutions. So I want to remind you here is RD is a parameter which is independent of late time physics, or I would say it is not much dependent on dark energy because it is a parameter like how much the baryon photon moves till the recombination. So it is more governed by the early time physics. On the other hand, H0 can be completely model independent, measured from the low redshifts. So these two cosmological parameters provide absolute scale for distance measurement anchors at opposite ends of the observable universe. So let's talk about these questions. So is H0 tension from BAO correlated with any other cosmological parameter? Yes. So BAO measures the combination of RD into H0 and not just H0 or RD. So can we break this degeneracy of RD into H0 and how we can do that? So if we know the H0 measurement by completely model independent way, and if we insert that value here, we get a value of RD completely independent from the high redshift or CMB observations. So we can measure the value of RD completely for low redshift observations. So we did that, and we have used BAO data. So this is like around 5 years ago. So we were using BAO data, which is from 6DF, MGS, eBOS, and BOS. And we were also using time delay distance measurements from Holy Cow, then angular diameter distances from Mega Measure cosmological project. Then we were fixing the value of H0 from cosmological model independent way. We were taking Rees 2016 value, and irrespective of the dark energy behavior taken, which is lambda CDM, WCDM, and CPL, we were getting the value of RD much lower than what Planck gets. So in Planck, the value of RD is around 147.5 megaparsec, and we were getting this value of RD around 135 or 139. So we measure a value of, sorry, there will be RD 136. And irrespective of dark energy behavior, we also checked in a completely model independent way by taking pad approximation, and we get the similar results. And we can see this references in these papers. So the results, so you can see here, this is the value, this dotted gray band is from Planck, and our results when we fix the H0 from Hughes measurement and the RD from completely low redshift, we get the value of RD more than 2.5 sigma away, irrespective of the dark energy behavior. Our results are quite model independent, and the price of shift in Hubble constant is the shift in RD. So you can see here, if we are having the value of H0 around 67.37 and the local measurement H0 is bigger, then corresponding RD we require is, for higher redshift we require higher RD, for low redshift we require lower value of RD. So to find early universe solution like Hubble or to increase the value of Hubble constant at high redshift, we need to decrease this value of RD to around 135, 139. And what does it mean to decrease the value of RD? So RD is, so if we go into the physics of it, what is RD? So RD is just a distance till which the baryon photon fluid travel together till recombination. So RD is just a distance, and distance is just velocity into time. Since the fluid was moving with acoustic speed, so here we have Cs, and then this is just time multiplied by the scale factor. So this is just velocity with which the baryon fluid was flowing till the recombination. So how can we decrease RD at higher redshift? One way is to change ZD. Another way is to modify the speed of sound. But speed of sound in ZD, they are very well constrained from BBN. So there is no room to change around much there. Another way is to decrease the age of the universe at the drag epoch. And that's where early dark energy came in. So one can decrease the value or decrease the age of universe by increasing the value of H0 or inserting early dark energy. So around that time, the expansion has happened more because of the early dark energy. So the conclusion of this work was, along with the Hubble tension, there is a similar tension involving sound horizon at the drag epoch from low redshift and Planck measurements. It does not depend on dark energy behavior. RD is gone by the early universe physics. To reduce RD or to increase H0 around recombination, one needs to modify the early universe cosmology or maybe need to introduce the early dark energy. Maybe you're familiar with these plots. So these results were also seen around the same time, 2016, with Bernal-Verde-Rees. And we can see here this, because of this magenta contour plot is coming from just standard distance ladder, because it measures a product of H0 RD and not just H0 or RD. And this gray band is from shoes. So by combining baryon acoustic oscillations and shoes, we get a smaller contour. So, and if we want to decrease the value of H0 around this, then we need to decrease the value of RD as well, as seen from this. So if we need to increase H0, we need to decrease the RD. So similar studies have also been seen by in another paper in 2019 in Hubble Hunter's Guide. I also want to stress one more thing here is you can see the correlation of H0 RD from low redshift observations such as BAO. It is in opposite direction to the correlation with CMB because of they are at different redshifts. So we can see here if we want the value of H0 to be higher, we require lower value of RD, which means we need to introduce some early dark energy solutions. So since now we are convinced BAO is really good probe and it can help to break the degeneracy of H0 RD and can tell where we should look for the solutions for addressing the cosmological tensions, now we can see what is happening within BAO because they are exactly at the same redshift. So in this work, I reviewed the anomalies in 2D and 3D BAO dataset, and I also included DESI results. So the data I used was supernova, type 1a supernova from redshift 0.01 to redshift of 2.3. Then I used 3D BAO and 2D BAO datasets. In 3D BAO, I have used the Bose sample and 6DF MGS. In 2D BAO, I have used this sample. You cannot read, okay, SDSS and DR10, data release 11. The observables that I use is for supernova, we have luminosity distance. And it does depend on cosmological model, but it also depends on this value of m, which is the absolute magnitude for supernova. And I wanted to make this study not depend on supernova, but mostly on BAO. So not to complicate the things, I only considered lambda CDM model and MB, taking all the possible MBs to see that my results are not biased by supernova or a cosmological model. So we can see here, these are the observables here, angular diameter distance for 3D BAO and theta BAO for 2D BAO. Now, how much these BAO results are fiducial cosmology dependent? So in 3D BAO, what one measures is the shift parameter, how much we are having the shift from fiducial cosmology in the transversal scale and in the longitudinal scale. On the other hand, 2D BAO is less model dependent in the sense that what they try to measure is the theta within the different over densities, but where does it have the fiducial cosmology is, since they can have many theta bumps, a theta bump is expected from the theoretical by putting lambda CDM, and they try to come towards that theta expected. So they are biased in that sense. So then the results that I got is, so you can see here on the x-axis, I have chosen different values of H0 or MB because I'm using supernova samples. On the y-axis, I have H0 RD because it is what BAO actually measures. And the green band is from CMB and the orange band is coming from DESI BAO. The teal color error bars is when I get the 3D BAO, which is the standard BAO, which I was talking with all the results before, which requires early dark energy. And now we have 2D BAO. We can see within 1 sigma 2D and 3D BAO, they overlap, but they are very far from what CMB measures. So 2D BAO is measuring the value of H0 RD much higher than what 3D BAO measures or what DESI sees. Also, if I look into this contour space, which is H0 RD and omega m0, we can see a complete discrepancy between these two contours. When we are taking different contours from 2D and 3D BAO, we can see this complete discrepancy. So, is it indicate that there is trouble to the standard cosmological model because this fiducial cosmology is going in both of them, and that is why they are discrepant with each other? Or maybe when they are inferring the BAO, they are not going very far away from lambda CDM, and maybe they require more cosmological model independent approach like profile likelihood or what Stefano was talking in the morning. So, then I also included DESI results here. So, we can see since I am using all 1700 samples of supernova and not 1550 which the DESI people have used. So, my contours are shifted in the second contour here, but they are still allow the dynamical dark energy model and more than 2 sigma away from the lambda CDM. But here very important thing is what I would want to stress is this green horizontal band is the sound horizon coming from CMB. In the 3D BAO, as I was saying, 3D BAO prefers the value of RD much lower than what Planck is getting. We can see here, but 2D BAO matches with the CMB RD value. So, something is there in the 2D BAO data different from 3D BAO data, even though they are the observation at exactly same redshifts. So, RD obtained from 2D BAO is compatible with the Planck RD, which is the higher value and higher H0. So, we are having higher H0 here and we are having higher RD, which was not the case with 3D BAO. So, it is an artifact because we are measuring the value of H0 RD bigger in 2D BAO, and that is why since the whole product is bigger, I can have higher H0 and higher RD. So, this is completely visible here, clearly visible here. So, this is value of RD in 3D BAO. These are the value, and all these value of on the x-axis are H0 from low redshift measurements. So, they are all higher value of H0. In 3D BAO, we require RD to be around 135, which I was saying, and which requires early dark energy. But in 2D BAO, they are already very near to the CMB RD. So, my conclusion is here what not to conclude and not what we should conclude. So, the main result is RD obtained from 2D BAO is compatible with Planck RD and higher H0. That is why when we are proposing solutions for cosmological tensions, we should be very cautious while using 2D BAO dataset. So, if like we are proposing a model and we are saying we are getting a value compatible with shoes and we are getting a value compatible with Planck, we are even getting that within lambda CDM framework. So, we need not to stress, okay, with this model I am able to do this, because it is even within lambda CDM that we are getting higher value of H0 and higher value of RD. So, final takeaway from this work is 2D BAO measures H0 RD higher than 3D BAO, and DESI analysis under standard lambda CDM cosmology using 2D BAO, higher H0 compatible with shoes and higher RD compatible with Planck can be achieved even within lambda CDM framework. Caution must be taken while concluding about the cosmological tensions, especially while using 2D BAO dataset, And while interpreting the omega m0 h0 RD plane, it may require physics beyond lambda CDM, or maybe there is systematic in 2D BAO data or 3D BAO data that at present I don't know. So future directions is we need to analyze more 2D and 3D measurements from upcoming surveys such as DESI, Euclid, JPass, which may provide us a better and bigger picture. And one can benefit from less model-dependent approaches while utilizing BAOs such as fiducial cosmology away from lambda CDM, which Stefano was talking in the morning, and or taking profile likelihood approaches, so which may help to bring both these 2D and 3D BAO data set closer, and then it can help in actually alleviating other tensions. Otherwise, we will be just looking at different different BAO data set and saying something about cosmological tensions. And thank you.
Excellent. All three. I see one. Okay, I see two questions there.
Okay, thank you for interesting talk. I would like to remind you and all that now we have 5 sigma evidence for strong progenitor age bias in supernova cosmology, which is composed by a set party. So now if that is taken into account, that the combination of revised supernova data set and the DESI BAO and the CMB combined is 6 sigma away from the LCDM. So we have several posters on it. So we can discuss that later.
Yeah, sure. That'd be great.
Hi, thank you for the talk. So very quick, so you have this discrepancy between your observables in your constraints. So can you just elaborate a bit more on the cosmology dependence of 2D BAO and 3D BAO, just to try to understand as well, like how much this can be influenced by that?
Okay, sure. Okay, so in 3D BAO, what we measure is the shift parameter. So we don't measure dH by RD or dA by RD. So what we measure is dH by RD upon dH fiducial by RD fiducial. So how much these peaks are shifting, then the fiducial cosmology. Okay, so what fiducial cosmology goes into the picture, and okay, so if one is taken lambda CDM, and how much they go far away from it, and if we are taking completely different model, and the model itself may lie very far. So as when the Stefano talk, it was there that in the right cosmology, you may see it as a sphere, but in the wrong cosmology, you can see it as ellipse, right? So the cosmology that is in the here, fiducial cosmology, is really important. That's why you can even see how the shift, you want to shift according to that particular geometry or different geometry, right? And in theta measurements, what you are measuring is the theta between the overdensities, right? So they are just seeing the overdensity, they are measuring a theta, but they are having many corrections which need to be find the exact signal of theta BAO. But how do they find the exact signal? They try to do what should be the expected theta, and then they are biased toward, okay, this is more coming close towards that, so maybe this is the theta BAO. But I'm not the person who does that, so maybe I can be wrong. Please feel free to correct me if I am. Thank you.